Woohoo, welcome back. Tonight we're going to be working with graphing functions using tables of values. And I'm going to set up some mood lighting here so that we've got fewer shadows so we can go ahead and graph some functions. So when we're graphing functions, it's going to look a lot like when we were graphing things we didn't know were called functions. Basically, you're going to look at the expression, and in this case, it's f of x equals x cubed. And you're just going to think of it as being just plain old y equals x cubed. And then just take a look at that and see if you know what it's going to look like. And x cubed has some interesting aspects. For example, you may recall that when we cube a negative number, it stays negative. So it's not like a square. Cubes are different. So that's going to tell us something about the shape. We also know that this is generally has no trouble with its domain. Cubing a number is fairly straightforward. So we're not like taking the square root of something or putting x in the denominator. So this is going to be a fairly smooth graph. But beyond that, you might not have an idea of what it looks like, and that's fine. So we can go ahead and just set up a table of values. If you do not know what a graph looks like, you should have a longer table of values, right? You need more information. So let's go ahead and give it a try. I would always start with 0 because I find that the intercept is always interesting. And y, which is x cubed, that's just 0 cubed, which is 0. So we've got the origin. Woo, so fancy. And then I'm going to look at, I happen to know something that's interesting about this. I'm going to look at 1/2 because I know what's coming. So 1/2 cubed, remember that's 1 cubed over 2 cubed, right? You can split up the cubes and that becomes 1 over 8. Okay, so that's interesting. When x is 1/2, y is very small, 1/8, much smaller. What about when x is 1? And when x is 1, y is 1 cubed, which is 1. Okay, that's expected. And when x is 2, y is 2 cubed. That's 8. And I could keep going. For example, I could do 3 or 4, but that's going to require a graph that's much bigger than this. So I'm going to have to decide how to graph this. This will be interesting. I don't have a lot of wiggle room. The next number I want to try is negative 1/2. Negative 1/2 cubed is negative 1 cubed all over 2 cubed, which is negative 1 over 8. And a lot of people ask, wait, how did you know to put the negative 1 on top? And the answer is you get to choose. So if you wanted to, you could make this 1 cubed over negative 2 cubed, but we'd still end up with a negative 1/8. Doesn't matter whether the negative goes to the top or the bottom, we get a negative. So we get negative 1/8, and then negative 1. Again, negative 1, the quantity cubed. There are 3 negatives, 3 minuses, so that's going to be a negative 1. Okay, that is what I'm going to graph because I happen to know, for example, if I plug in negative 2, I am going to get negative 8, but I happen to also know that I don't have enough space on this to fit both 8 and negative 8 on it. So let's take a look. I'm going to count. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So what I'm going to do is I'm going to go ahead and put my x-axis down here. I'm going to give a little bit more space above the x-axis. And since I'm doing the same thing left and right of the y-axis, I'll go ahead and put the y-axis just about in the middle, close to. And this is my y. Obviously, you can always look for a bigger piece of graph paper, but I thought it would be interesting to play with what it's like if you're limited to how much space you have. Let's see if we can get an image of this. So just with the table of values, I see that when x is positive, y is positive, so I'm going to be over here. And when x is negative, y is negative, so I'm going to be down here. So I'm going to be in the first and third quadrants, which is good to know. You don't know the word yet, but this is going to be an odd function. That's something we're going to look at later on. And that basically means when x is positive, y is positive. When x is negative, y is negative. So in other words, negatives stick around. And as you might have guessed already, when you have something like x squared, that's called an even function. Y is positive or 0 no matter what. Okay, so I noticed these things. I'm going to go ahead and graph. I've got this very uncomfortable to graph 1/8 and negative 1/8. I'm just going to bunt. And there's 1, there's negative 1. I got 1, 2, 3, 4, 5, 6, 7, 8. And then can't go much further down here, but obviously my negative 8 would be down here. So it's something to keep in mind. 1, 2, negative 1, negative 2. I've got the point 0, 0. I'm going to skip this for right now. I've got the point 1, 1. I've got the point negative 1, negative 1. Right there. And I've got the point 2, 8. And now I can already see this is not linear, right? These 3 points do kind of look linear, and I could draw a line through them and I would have the wrong graph. So be really careful. Always make sure you're checking lots of points when you don't know what the shape is going to be. And I can see that a straight line would go through these 3 points, but not through this point right up there. And so I'm going to have a curve, obviously. And then I would also have another point down here, kind of a ghost point. That's not where it would actually be, but I can kind of wiggle it in. That's about where it would be. So that'll give me a kind of sense. And hopefully from that, you kind of start to see the shape. And then we've got this other really interesting point that I'm plotting some fractions, and this is going to be the uncomfortable truth, which is you should plot some fractions if you don't know what the graph looks like, just to see if it does anything wacky, and it does. So x equals 1/2 is right in the middle, right there, but y equals 1/8 is just barely above. So this point is going to be right there. Really close to the x-axis, but halfway between 0 and 1. I know I seem to have had an ink explosion, but I can still graph. It's not going to stop me. When x is negative 1/2, which is over here, halfway between the 0 and the 1, y is negative 1/8. So that, again, very close to the x-axis, but just below it. And that gives us an indication of the shape, because the shape does a swoop up here like this, and this is something that you won't necessarily know the name yet, but I'm going to give it to you. This has to do with the concavity, how concave it is. Does it open up like a bowl, or does it open I can't do it. Does it open down like a frowny face, or does it open up like a smiley face? And this part is kind of half of a smiley face. And this part over here is a frowny face. So it's kind of interesting. This graph, f of x, and now that we know the name, it's f of x, I could just write f of x. I could leave it like that, or I could give more information, f of x equals x cubed. It's up to you. That's how we graph it. And then, of course, I recommend that when you're going through this, as you're practicing in 2.2, you won't necessarily know these graphs. So check them out in Desmos. Remember that you have this amazing free reference, Desmos. Okay. Woohoo! Shall we try graphing a second point? Yes, let's graph another one. Yay. Dun, dun, dun. Now, as promised, I think in the very last, well, in a recent video, I promised you that there would be an exciting piecewise defined function. This is a piecewise defined function. This is some wacky stuff. So let's take a look at what's going on. And let me see if I can find those. I forget what order I used the colors in. But basically, I'm going to pull out some colors to help. If it helps, that's awesome. I've got I'm going to call this the pink part. X is less than 3. And then I've got the yellow part. X is between 3 and 6. And then this part, if X is greater than 6. Okay, and this is called g of x, and I've got pieces. Now, I'm not going to lie. If you don't already know the shape of these, it's going to be a lot harder. So the first thing you should probably do is think about what the shapes of these, just without this part, just what are the shapes of these. So let me talk about these. Y equals x squared is the one that might be the most unfamiliar. Some of you may never have graphed something like this. And x squared is a parabola. Looks like that. It opens upward if it's x squared. If it's negative, it opens downward. Y equals 9 is just a horizontal line. And then y equals 2x is a line with slope 2. So it goes up and it's slightly slanted more than just y equals x. So it may actually be a little bit steeper than that. But basically, those are the basic shapes. And so what are we going to do? Well, we're gonna create a Frankenstein's monster of these. We're going to cut part of the x squared. So we're going to take a piece of the x squared for all points less than 3. Then we're going to take a piece of the 9 for the points between 3 and 6. And then we're going to take a piece of this for whatever x is greater than 6. So there are a couple of different ways to do this. The easiest way to do it, since you guys are not in the room with me, so I can't interact with you, is to go ahead and set up a table of values. So I am going to set up that table of values. And I'm going to break it down. I've got less than 3, between 3 and 6, and greater than 6. So I'm going to go ahead and do 0, 1, 2, and then 3, and then 3, and then 4, 5, 6, and then 6. I should put these both in parentheses, and then 7, and that's as far as I'm going to go for right now. Also, I will point out that for this one, I'm probably going to have to deal with, oh, you can't see. I'm pointing to something you can't see. For this one, I'm going to have to look at some negatives, but I wanted to keep it simple to begin with. So let's take a look at what's going on. So this says if x is less than 3, that is this section. Now, you're going to notice this says strictly less than 3, and yet I'm including a 3 in the pink world. And remember, when we did piecewise defined functions before, there is no number right next to 3. So what I'm going to do is I'm going to say, let's pretend 3 was actually included in this set. Where would it be? So let's see. I've got, for these 3, I'm in pink land. So this is going to be x squared, right? Less than 3. So this is x squared. So I get 0 squared, which is 0. This is also an x squared. 1 squared, which is 1. X squared. 2 squared, which is 4. And then 3, oops. I should follow, be consistent. I jumped the gun, I got so excited. And then again, I'm breaking the rule a little bit. I'm just saying, what if 3 were included? That would be 3 squared, which is 9. Which is interesting, because in the yellow portion, between 3 and 6, and here I'm regretting that I made this so big because it doesn't all fit, but you're going to have good memories. Up here for the yellow section, I start at 3. 3 is included. Notice the 6 is not included here. It's also not included here, which is kind of interesting. Piecewise defined functions are funky. But I'm going to look both at 3 and at 6 and say, what if 6 were included? And the rule for the yellow section, the middle section, is really nice and easy. It's 9. It's a constant function. So 3 is 9. 4 is 9. 5 is 9. 6 is 9. Oh, so easy. Okay. And then I'm in blue land. So again, 6 is not included, but since it's right on the boundary, I'm going to see where it would be. And I'll show you how I'm going to use this. So if you're like, you can't just go and do that, the answer is my table of values can have anything I want. They aren't necessarily all going to be graphed, but I can collect any sort of data I think will help me out. So the rule is 2x for the blue land. So over here, oh, I can keep this up. There we go. This will be 2x, which would be 2 times 6, which is 12, and 2x, and that would be 2 times 7, which is 14. So I've got a bunch of data points. That's very interesting. So what I'm going to do is I'm going to figure out how I'm going to graph all of this. So the first thing I notice is that for all of these points, I don't have any negatives. So I'm going to say, oh, okay, I should probably try some negatives. What if x were -1? -1 is less than 3. That is in pink land. If x is -1, I've got x squared, which means I've got -1 squared, which is 1. If x is -2, I'm also in x squared land. -2, the quantity squared is 4. And then I realize, oh my goodness, all of the y values are going to be either 0 or positive. So that makes things a little bit easier because I'm just going to put the x-axis down at the bottom, because I'm not going to use any negative y values. I also see that the way that I've gathered my information here, most of the points are going to be to the right of the y-axis, right? I'm going from 0 to 7 on the right-hand side, but only -1 and -2. So I'm going to put my y-axis right here, like that. And this is a choice. And again, I'm showing you what to do if you've got a limited amount of space. If you have a whole grid page, use it. Use it. Put everything into it. That's awesome. Okay, so having said all of that, woohoo, let's go ahead and see what we can get out of this graph. So the pink part of the graph, I've got the point 0, 0. I've got the point 1, 1. And then I think about it and I'm like, oh no. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Ooh. What mistake did I make? If I'm going to have to get up to 14, oof, I'm going to wipe that out. Really, since I have to get all the way up to 14, I should probably count by 2s. So let's try that. 2, 4, 6, 8, 10, 12, 14. Okay. And I'm gonna go ahead and, you know, I'm feeling wild and crazy tonight. I think I'm gonna count by 2s in the x direction. Ooh, this is exciting. This is a choice. It isn't necessarily the best choice, but it's an interesting choice. So let's go with it. Let's see what we can do. So let's try this again. I got 0, 0, 1, 1. There's 1 there. There's 1 there. So it's going to be right smack in the middle. I've got 2, 4. And then 3, 9. Notice this isn't actually included. So what am I going to do? Well, for 3, I'm going to go up to where 9 would be, and I'm going to draw an open circle. Okay, so that's the beginning of the pink part. And then I also have this point -1, 1. Uh-oh. Well, unfortunately, I've got a 1 written in right there. So I'm going to put the 1 right there. And then I've got -2, 4. -2, 4 goes up there. Now, from these, I drew this up here for you. It's a parabola. Can you kind of see that for the pink part, this is going to be, it's going to go up like this, and it's going to go up like that. Now, it looks a little pointy at the bottom. That is one of my fatal flaws, is I can't make the bottoms of my parabolas look as round as they should be. Sometimes I go back in and I kind of wiggle them more round. So that's that part. Okay, so that's the piece of the parabola. Woohoo. Now, the yellow, the middle, the constant function between 3 and 6, including 3, but not including 6, we've got 9. So I've got a point here at 3, 9. I've got a point at 4, 9. I've got a point at 5, 9. And I've got a point at 6, 9. And notice that for the 6, that is not included, so I've got an open circle right there. And that's the yellow piece. Ooh, I'm going to go to Smeary Land. There we go. So I've got a function that comes down, goes up, pretends to be a parabola, and then it goes sideways. And then I've got this interesting thing that when I'm at 6, I should be up at 12. So I do this big jump up to 12. Notice that it is not included. Not included. So open circle here. Not included. And then 7 corresponds to 14. And in fact, I might go ahead and say, you know what, I want to draw one more there because I'm not really sure where this is going. So let me give it a couple more because this says anyone greater than 6. So I could choose 8. And that's going to be in 2x land. That'll be 2 times 8 is 16. And 9, that'll be in 2x land. 2 times 9 is 18. So I can come over here and I could say, okay, so for 8, I'm at 16. And for 9, 9 goes right in the middle there, I'll be at 18. So it'll be right there. And interestingly enough, those are all lying in a straight line, which is what we're expecting here, right? This is this straight line for the blue section. So the blue section looks like that and goes up like that. Again, this is, oof, that's so smeary. This is the yellow part. And then this is the pink part. What do you think? Now, some interesting things to notice. Is this a function? Yes. I can use the vertical line test and see that a vertical line does not pass through more than one point. Any vertical line I have goes through a single point. But there is an interesting point. When x equals 6, this function's not defined. It's not there, and it's not there. And in fact, we're not told where it is. We're given no information. So for some reason, that data is missing. But we have a function that goes swoop-de-doop, scoosh over there, little Tokyo drift, and then kapow up there, if you want to have automatopoetic discussions of it. And that is our fancy piecewise defined function. Woohoo! So in the next video, we're going to come back and we're going to look at a few common shapes that you may or may not want to learn. And then we're going to go from there with yet more excitement. Woohoo! Are we very excited? I can tell you're excited. I'm excited. Go ahead and go get a break. Take a break. Get a snack. Get something to drink. Know that you're amazing and awesome. And I am so glad you are giving this all a try. And remember to ask questions and remember to math on.